This is the refrigeration presentation by Team 1 for the Mechanical Engineering Systems Lab at Georgia Tech. Team 1 is comprised of Kakeru Kobayashi, Yinan Li, Mason Randall, and Thomas Yocum. A special thanks to the course TAs, Alana Homa and Nicholas Miller, and to the course instructor, Dr. David McNair. A YouTube link to this presentation will be provided here upon video upload. Machine Chillers Incorporated has created a cooling system based on vortex tubes that uses air as its working fluid. As Burdell Inc. engineers, the team has been tasked with modeling the system in order to determine its capabilities and ideal operating conditions. Testing will be conducted over 2 weeks, with the first week focusing on the characterization of steady-state relationships, and week 2 will evaluate the system's transient response. This presentation outlines the results of week 1 data collection, as well as discussing the next steps of experimentation. Here is a snapshot of the system that the team will be working with during data collection. There are 5 measurement stations capable of measuring the temperature and pressure of the working fluid. Station 1 measures the compressed air. A heat exchanger between stations 1 and 2 cools the air to ambient temperature. Rapid pressure variation is removed between stations 2 and 3. And Station 4 separates the outputs into a cold and hot output. Station 5 then measures the output air just before venting it to the atmosphere.
For the first week, we will be focusing on the steady-state relationships. We want to cool a device using mechanical work. We want to determine the relationship between motor setting, system pressure, vortex tube's input-output properties, and heat energy transfer at the load. For this purpose, here are our experimental methods. The IC engine mentioned above will be the primary system that we will be using, along with a VI that takes the input into a computer for us to analyze the data. We start with ambient temperature and collect offset values. Station 1 will compress air through a heat exchanger to pressurize air pulses and cool the air. Then, this air is put into a simulator tank to create constant pressure. The air is then flown into a vortex tube to separate hot and cold compressed air. Hot air will be vented, and cold air will be used to cool the load. Run the system with a motor input voltage of 0, 0.5, 0.5, 1, 1.5, 2, and 2.5 volts until the system reaches steady state. With this data, we can model the steady state relationship between input voltage and pressure. For week 2, we will model the transient cooling of the load while being cooled by building air and by the compressor. We will be doing the same procedure, but with a compressor at around 40 psi and 80 gauge instead of having voltage as inputs. With this data, we can calculate the load energy balance for each transient response.
From the collected data, the data of the input voltage and pressure from compressor was expressed as a second-order polynomial, as you can see it in the plot. The equation shown in the plot was generated from the MATLAB using polynomial field function. This equation is used for the transient experimental analysis to calculate the input voltage from the desired pressure flowing through the load. Comparing a temperature from vortex tube and pressure from compressor, the temperature on the cold side of vortex decreases with increasing pressure and have a third-order polynomial relationship with pressure. The polynomial relation was generated so that it could pass all the data with ellipses, representing the uncertainty of each data point. On the other hand, the data points on the temperature from hot side of vortex can be expressed as a linear regression. As more pressure goes in, the temperature on the hot side gets increased. Next, the mass flow rate and pressure from compressor were compared. On both cold and hot side of vortex, the mass flow rate can be expressed as a linear regression, passing through all uncertainty ellipses. Those plots indicate the mass flow rate increase as the pressure flowing in the vortex increase on both cold and hot sides. Next, the temperature from compressor is supposed to match with the ambient temperature. Comparing the experimental data of temperature from compressor and ambient temperature for each input voltage case, It turned out the percentage difference increased as the input voltage increased, and it maximized at the highest input voltage 2.5 voltage. Those data indicates that the heat exchanger and accumulator work well at lower input voltage. Comparing the pressure before and after flowing through the load for each input voltage case, the difference between them was small. Those values are supposed to match in our assumption, so those values means we can use some dynamics assumption for energy calculations on the load.
As we move into our heat transfer rate calculations, it is important to understand which points we are interested. For this section, we'll be looking at the load of the system and analyzing temperatures at T4, T-load, and T5. We are especially interested in the T4 cold side of the vortex tube, as that is our main source of our cold air going into our load. For these calculations, it is important to note that we are in steady state. This means that the first equation in the top right can be simplified to Q air is equal to Q ambient, meaning that we solve for the power input to our system by the environment. In order to do this, we must first calculate the insulation thermal resistance, using the second equation in the top right, where K is the thermal conductivity of our material, A is the surface area of our load, and L is the thickness of our insulation. Using this and the relationship of the thermal resistance to heat transfer rate, we found that our thermal resistance was 8.4 Kelvin seconds per joule. Our theoretical was 15 Kelvin seconds per joule, which is a difference of 46%. This is due to the imperfect insulation, as much of the load was not covered by the styrofoam cover. This includes the copper rods connecting the load, cuts in our insulation, and many other imperfections. This heat transfer is found with the relationship of the third equation, and the air propagation from the thermal resistance calculations is included in that heat transfer rate, as the calculated value is 0.95 watts and the experimental value that we found was 4.059 watts. Overall, the majority of our points fall within our uncertainty bounds and fall in line with expected values, as the positive wattage shows the input of energy to the system by the environment.
The voltage-pressure relationship is shown here. This equation was determined based on the data collected during week 1 and will be used in order to determine the voltage input to be used for the 40 psi case in the second week of data collection. A notable result from the first week of testing showed that the difference in T3 and T ambient increased as the input voltage increased. The difference in P4 cold and P5 was also notable, in the way that the differences were scattered for varying input voltages, and the pattern is not as linear as what is seen with T3. The experimental Rin value was calculated to be 8.0479 kiloseconds per joule. This value is relatively far off from the theoretical, and further analysis will be undertaken to determine exactly why.
Some of the larger takeaway points include the insulation used to maintain ambient temperature in the load. The foam insulation does not necessarily provide perfect conditions, therefore there's a lower normal thermal resistance which may be contributing to some of the values different from the theoretical. Additionally, a positive Q ambient indicates that there is energy entering the system, which could also be a cause of the imperfect insulation. The team is interested to see the results of this week's data collection when compared to the data including the system's transient phase.
The next steps in data collection will focus on capturing similar variables as week 1. However, week 2 of experimentation will capture the data in a transient state, as opposed to the steady state data that was collected during week 1. The voltage-pressure relationship discussed previously showed the team that an input voltage of approximately 1 volt would be required to run the system for 40 psi. A compressor will then be used to collect transient data when the pressure gauge reads 80 psi. Finally, these equations outline the process that will be undertaken in order to evaluate the change in energy that is being experienced by the system. Thank you for taking the time to watch Team 1's progress presentation for the refrigeration lab that is being undergone as part of ME 4056 at Georgia Tech. Any questions can be directed to the team through the course team channel. This slide details the references that were used in order to further the team's understanding of relevant concepts, to compile information on the system being used for data collection, and to complete relevant calculations.